What if reality itself shifts the moment we look at it? Picture a universe where particles don't settle into a definite state until someone or something observes them. It sounds like science fiction, but this is the heart of one of quantum mechanics' most bewildering puzzles, the measurement problem. And here's the twist: this isn't just some abstract thought experiment confined to labs. It might hold the key to understanding the very fabric of the cosmos, from the tiniest particles to the vast expanse of galaxies. Now, imagine this: every time you glance at the stars, you're not just a passive observer. You're part of a grand, mysterious dance where the act of looking could be shaping reality itself. This idea isn't just mind-bending, it's revolutionary. It challenges everything we thought we knew about how the universe works, and it's forcing us to ask bigger questions. What does it mean for our place in the cosmos? How could this principle unlock futuristic technologies we've only dreamed of? And most importantly, why should you care about a problem that seems buried in physics textbooks? That's exactly what we're diving into today. The measurement problem isn't just for scientists in white coats. It's a gateway to understanding how reality might be far stranger and far more interactive than we ever imagined. From quantum computers that could revolutionize industries to the possibility that consciousness itself plays a role in shaping the universe, this mystery stretches far beyond the lab. So, if you've ever wondered whether there's more to reality than meets the eye, or whether your observations might somehow matter on a cosmic scale, then you're in the right place. Because by the end of this, you won't just see the universe the same way again. You'll question what it means to look at it in the first place. At the smallest scales of the universe, particles don't behave like tiny marbles with fixed positions. Instead, they exist in a haze of possibilities, what physicists call a superposition. Think of it like flipping a coin before it lands. While it's spinning in the air, it's not just heads or tails, it's both at once. Only when it hits your palm does it become one or the other. That's essentially what happens in the quantum world, but here's where it gets wild. The coin flip doesn't resolve until something, a detector, a lab instrument, or even a conscious observer, checks the outcome. This is the measurement problem in action. Take Schrödinger's famous and slightly morbid thought experiment, a cat in a box with a quantum-triggered poison. Until you open the box, the cat isn't alive or dead. It's suspended in both states simultaneously. The moment you peek inside, reality snaps into place. Sounds absurd, right? Yet this isn't just a quirky metaphor. Lab experiments with electrons, photons, and even entire molecules confirm that quantum systems genuinely hover in this ghostly in-between until measured. What's truly unsettling is how this upends our everyday intuition. We're used to a world where objects have definite properties whether we're looking at them or not. A tree falling in the forest makes sound waves even if no one's around to hear it, or so we assume. But quantum mechanics suggests that at its core, reality might not work that way. There's no tree or sound until an interaction forces the universe to pick a version of events. Now here's the cosmic twist. If tiny particles need an observer to settle into reality, could the same rules apply on a grander scale? Could the universe itself be shaped by observation? It's a question that blurs the line between physics and philosophy. One we'll explore next as we push beyond the lab and into the stars. When we zoom in on the quantum realm, the Copenhagen Interpretation offers one of the most provocative explanations for the measurement problem. Pioneered by Niels Bohr and his colleagues in the 1920s, this framework suggests something extraordinary: reality doesn't solidify until the moment it's measured. It's not just that we discover a particle's position or spin. The act of observation creates those properties. Think of it like a cosmic game of 20 questions, where the universe refuses to commit to an answer until you ask. This idea doesn't just rewire how we see particles, it reshapes our entire understanding of existence. If reality hinges on observation, then consciousness isn't just a passive bystander, it's an active participant in shaping the cosmos. Bauer himself wrestled with the philosophical weight of this. If a tree falls in a forest with no one to hear it, quantum mechanics might reply, does it even fall at all? Without an observer, whether human, animal, or even a machine, the event remains suspended in a haze of potential outcomes. Now, fast forward to today, and this raises jaw-dropping questions about the future. If consciousness plays a role in collapsing quantum states, what happens when artificial intelligence enters the picture? Could a sophisticated enough AI designed to process and observe quantum data become a cosmic actor in its own right? We're already building quantum computers that exploit superposition to solve problems in seconds that would take conventional machines millennia. But what if these machines don't just compute reality, they influence it? The implications ripple outward, from encryption that changes when monitored, to experiments where AI observers might alter outcomes simply by looking. Critics argue this veers into metaphysics, but the math doesn't lie. Experiments like the double-slit experiment, where particles behave as waves unless measured, then choose a particle-like path, keep confirming the bizarre link between observation and reality. Even if the Copenhagen interpretation isn't the final word, it forces us to confront a universe far more interactive than we ever dreamed. Whether the ultimate observer is a human, a machine, or something beyond our current grasp, one thing's clear: the cosmos might not just exist. It might be listening. But what if the universe doesn't choose just one outcome when we observe it? What if, instead of collapsing into a single reality, every possible outcome happens, each branching into its own parallel world? This is the radical alternative proposed by physicist Hugh Everett in the 1950s, known as the many worlds interpretation. Forget the Copenhagen idea of observation forcing reality to pick a side. Here, the quantum coin never lands, it splits, spinning off into two separate universes where both heads and tails exist simultaneously. This isn't just theoretical sleight of hand. Everett's math suggests that every quantum decision, every particle's wiggle, every atom's flicker, spawns new timelines. When Schrödinger's box is opened, there's no spooky superposition. Instead, one universe holds a living cat, another a dead one, and neither is aware of the other. It's a cosmos of infinite branching paths, where every what-if plays out somewhere. Pop culture loves this idea. Films like Everything Everywhere All at Once vividly capture the chaos and wonder of a multiverse. But beneath the sci-fi spectacle lies a startling possibility. If many worlds is correct, quantum computers aren't just crunching numbers in this reality. They might be harnessing the computational power of countless parallel versions of themselves, exploring solutions across universes we'll never see. Imagine a machine that doesn't just calculate outcomes but accesses them, borrowing answers from branches of reality where different choices were made. Critics argue this is untestable. How do you prove the existence of worlds you can't interact with? Yet recent advances in quantum computing hint at something eerie. When qubits perform calculations, they exploit superposition to explore multiple solutions at once. In many worlds' terms, they're not just simulating possibilities, they're briefly touching them. It's as if the machine is peeking into adjacent realities, gathering data from versions of itself that took different paths. Whether you find this exhilarating or unnerving, one thing's certain: the many worlds interpretation doesn't just change how we see quantum mechanics. It redefines what it means to exist. If every measurement births new universes, then you right now are constantly splitting into countless versions of yourself, each living a life shaped by infinitesimal quantum choices. The cosmos isn't just stranger than we imagined, it's stranger than we can imagine. What if reality doesn't need an observer at all? What if the universe has its own built-in mechanism, a cosmic failsafe, that forces quantum possibilities to snap into place without anyone watching? That's the bold claim of objective collapse theories, which propose that wave functions don't wait for human consciousness or even machines to collapse. Instead, they fall apart all on their own. One of the most intriguing models is the Gerardi-Rimini-Weber theory, or JRW for short. Picture this: tiny, random fluctuations in the fabric of reality itself occasionally nudge particles out of their fuzzy quantum states and into definite positions. It's like a cosmic game of musical chairs where the music stops unpredictably, forcing every particle to finally take a seat. Unlike the Copenhagen interpretation, there's no observer required. The universe simply tidies itself up spontaneously, preventing the quantum weirdness of superposition from scaling up to our everyday world. But here's where it gets even wilder. Some versions of these theories suggest space-time itself might be the trigger. Imagine gravity, the curvature of space-time caused by mass acting as a kind of quantum referee. When a particle's superposition becomes too heavy in terms of mass or energy, gravity steps in and forces it to pick a state. This idea, known as the Diosy-Penrose model, implies that Einstein's general relativity and quantum mechanics might be secretly working together to keep reality stable. Now, how do we test something this abstract? Scientists are getting creative. Future gravity wave detectors, like upgrades to LIGO or the proposed Einstein telescope, could hunt for faint ripples in space-time caused not by colliding black holes but by spontaneous quantum collapses. If these experiments catch even a whisper of such events, it would mean collapse isn't just a quirk of measurement, it's woven into the very structure of the cosmos. Think about the implications. If JRW or similar theories hold up, our universe isn't just strange, it's self-regulating. Quantum weirdness stays contained at the microscopic level because reality has its own cleanup crew. No observers needed, no parallel universes branching endlessly, just a cosmos that quietly resolves its own uncertainties like a puzzle solving itself in the dark. Yet the mystery deepens. If space-time truly plays a role in quantum collapse, could we one day manipulate gravity to control superposition? Might futuristic tech harness these spontaneous collapses to build ultra-precise sensors or even new kinds of computing? The line between fundamental physics and sci-fi keeps blurring, and that's what makes this search so thrilling. Whether these theories hold up or not, they remind us that the universe still has secrets tucked away in the quantum shadows waiting to be uncovered. But what if the apparent collapse of quantum states isn't due to observers or parallel universes at all? What if reality simply looks classical because the universe is too noisy for quantum weirdness to survive? That's the essence of quantum decoherence, the process where fragile superpositions get scrambled by their surroundings, making them seem to vanish. Imagine trying to hear a whisper in a storm. The whisper still exists, but it's drowned out by the chaos around it. That's exactly what happens to quantum particles when they interact with their environment. Take a single electron in a superposition spinning both clockwise and counterclockwise at once. In a perfectly isolated lab, this delicate state might persist. But out in the real world, random bumps from air molecules, stray electromagnetic fields, even the faint warmth of nearby objects constantly jostle the electron, forcing it to pick a direction. It's not that the superposition collapses into one state, it's that the quantum signal gets lost in the noise. The electron appears classical because its quantum phase relationships, the interference patterns that define superposition, are obliterated by environmental interference. This idea isn't just theoretical. Quantum computers live or die by decoherence. Their qubits rely on maintaining superposition long enough to perform calculations, but stray heat or vibrations can destroy that coherence in microseconds. Engineers fight this by cooling chips to near absolute zero, shielding them in vacuums and designing error-correcting codes. It's like trying to build a house of cards in a hurricane. Every outside interaction threatens to topple the entire system. Yet here's the irony: decoherence might also explain why our everyday world feels so solid. If every atom in your body was constantly in superposition, you'd literally blur at the edges. Instead, the countless collisions and interactions with your surroundings stabilize reality, acting like an invisible hand that selects classical behavior from quantum chaos. It's not that quantum physics stops working at larger scales. It's that decoherence hides the weirdness so well we mistake the illusion for reality. Now, what if we could control this process? Some researchers are exploring how to tune decoherence, using it to our advantage. By carefully engineering environments like tailoring noise to protect certain quantum states, we might one day build robust quantum systems that thrive in the real world, not just frigid labs. It's a reminder that sometimes understanding the universe isn't about removing noise, it's about learning to dance with it. Now let's stretch the measurement problem to cosmic scales. If observing a particle in a lab can force it into a definite state, what happens when we point telescopes at galaxies billions of light years away? Could the act of measuring starlight photons that have traveled across the universe somehow influence the quantum states of distant matter? It's a dizzying thought. Astronomers might not just be mapping the cosmos, but subtly shaping it. Consider this. When a telescope captures light from a far-off quasar, those photons began their journey eons ago, interacting with interstellar gas and dust along the way. Quantum mechanics suggests those interactions might have left the photons entangled with particles in distant regions of space. Until we measure them, those particles could still be in superposition, ghostly probabilities rather than solid reality. The moment the photon hits our detector, does it retroactively lock in the state of those ancient cosmic particles? Some interpretations, like quantum retrocausality, hint that the answer might be yes. This isn't just philosophical musing. Experiments in quantum optics show that delayed choice measurements can seemingly rewrite the past behavior of particles. In lab setups, scientists can decide whether a photon behaved as a wave or a particle after it's already passed through an apparatus, as if the present reaches back to tweak history. Scale that up, and you're left with a spine-tingling question. Does our observation of distant starlight today somehow ripple backward through time, crystallizing quantum uncertainties that floated unresolved for billions of years? Critics counter that decoherence likely washed out any quantum weirdness long before those photons reached us. Space isn't a pristine lab, it's a sea of radiation, gravity, and collisions that would have collapsed superpositions naturally. But here's the twist: what if some quantum fragility persists? Certain models suggest that vast, sparse regions of the cosmos, like the voids between galaxy clusters, might remain isolated enough to preserve delicate states. If so, our telescopes could be the first observers to touch these quantum relics, forcing them into classical reality across unimaginable distances. The stakes here are cosmic. If measurement truly influences the universe on this scale, then astronomy isn't a passive act. It's a participatory one, where the tools we build and the data we collect don't just reveal reality, they might help construct it. Imagine future telescopes designed not only to see deeper into space, but to test whether the act of seeing itself leaves fingerprints on the fabric of existence. It's a humbling reminder: when we gaze at the stars, we might not just be witnesses to the universe, we could be its co-authors. What happens when two observers witness the same quantum event and disagree on the outcome? That's the unsettling core of Wigner's Friend, a thought experiment that pushes the measurement problem into the realm of conflicting realities. Picture this: a scientist, let's call her Alice, runs a quantum experiment in a sealed lab. She measures a particle in superposition, and to her, it collapses into a definite state. But outside the lab, another scientist, Eugene Wigner, treats the entire lab, Alice included, as a quantum system. From his perspective, Alice and her measurement device remain entangled in superposition until he observes them. So who's right? Both? Neither. reality splits down the middle, with each observer locked in their own version of events. This isn't just a quirky brain teaser. It exposes a rift in how we define observation. If Alice's consciousness collapses the particle's wave function, but Wigner's consciousness is required to collapse hers, where does the chain end? Some interpretations suggest there's no objective reality, just layers of observers, each unknowingly shaping their own pocket of existence. Now, inject this into a future where artificial intelligence thrives. Imagine an AI lab assistant monitoring quantum experiments autonomously. When it records a measurement, does its observation carry the same weight as a human's? Or does it merely become part of another, higher-level observer's superposition like Wigner's friend, but coded in algorithms? The stakes get even stranger when you consider networked AI systems. What if thousands of quantum-linked machines simultaneously observe entangled particles across the globe? Do they collectively collapse reality, or does each spawn its own branch? Venture further, and you hit speculative but thrilling territory. Could future AIs opt out of classical reality entirely, engineering environments where their observations deliberately preserve superposition? Picture a quantum internet where sentient algorithms communicate through entangled states, bypassing definite outcomes altogether. Critics dismiss this as metaphysics, but the paradox forces us to confront a foundational question. What qualifies as an observer, consciousness, complexity? Or is it simply interaction? Labs are already testing scaled-down versions of Wigner's friend with photons and beam splitters, and the results are ambiguous. Reality seems to adapt to the observer's frame of reference, with no universal referee to declare a winner. So where does that leave us, in a universe where measurement might be less like flipping a switch and more like whispering into an echo chamber, where every observation ripples through layers of ambiguity, and the very act of looking could rewrite the rules? Whether the final word goes to humans, machines, or some yet unknown entity, one truth emerges: reality might not be a fixed stage. It could be a hall of mirrors reflecting back whatever or whoever dares to peer inside. Imagine reaching into the past and tweaking an event that's already happened, not with a time machine, but with a simple decision in the present. That's the eerie promise of delayed choice experiments, a class of quantum tests where what you choose to measure now seems to rewrite the history of a particle. The most famous of these is John Wheeler's quantum eraser, a thought experiment so counterintuitive it feels like it's pulled from a sci-fi novel. Here's how it works. A photon travels through a setup with two possible paths, like a fork in the road. Normally, if you don't peek at which path it takes, the photon behaves like a wave, creating an interference pattern, a hallmark of quantum weirdness. But if you place detectors to observe its path, the photon picks a definite route and the interference vanishes. Wheeler's twist: wait until the photon has already finished its journey before deciding whether to look at its path or erase that information. Astonishingly, the photon's behavior, whether it acted as a wave or a particle, appears to change retroactively, as if your choice in the present reaches back to alter the past. This isn't just theory. Labs have confirmed it using beam splitters and entangled photons. In one version, scientists can mark which path a photon took with a quantum tag, then later choose to either read that tag or scramble it. If they scramble it, the photon's history updates suddenly. It always behaved like a wave, and interference patterns reappear. It's as if the universe keeps its options open until the last possible moment, refusing to commit to a single timeline until forced. Now, stretch this idea across cosmic distances. Picture a quantum network where entangled particles are separated by light years, say, one on Earth and another near a distant star. If we measure the local particle today, does that instantly fix the state of its entangled partner, even if that partner's decision was technically made centuries ago? Experiments suggest the answer might be yes. In a universe where quantum connections transcend space and time, now and then blur into a single, knotted reality. Future tech could exploit this, building interstellar communication systems where measurements today send data into the past not by breaking causality, but by leveraging the universe's own ambiguity. Critics argue this is just a quirk of interpretation, that retrocausality is an illusion born from our limited perspective, but the math holds up and the implications are staggering. If delayed choice affects scale, then reality isn't a fixed tapestry. It's more like a draft constantly edited by future observations. Telescopes probing ancient starlight might not just be uncovering history, they could be finalizing it. Now here's the real question. If quantum systems remain unsettled until measured, could we one day build eraser technologies that selectively undo past observations? Imagine a quantum hard drive where deleted data isn't just wiped, it's as though it never existed in the first place. Or sensors so precise they let us rewind the quantum states of particles, effectively erasing their measurement history. The line between future and past starts to feel less like a boundary and more like a negotiation. Whether you find this thrilling or unnerving, one thing's clear: the universe seems to play by rules that defy our everyday logic. And the deeper we dig, the more it feels like time itself might just be another quantum variable waiting for someone or something to make up its mind. What if the universe itself acts like a copying machine, endlessly duplicating quantum data until reality finally snaps into focus? That's the heart of quantum Darwinism, a radical idea that explains why we perceive a stable, classical world despite the underlying quantum chaos. Think of it like a viral tweet. The more times information gets shared, the more real it becomes. In this case, the environment, everything from air molecules to starlight, acts as a relentless broadcaster, replicating certain quantum states until they're impossible to ignore while others fade into obscurity. Take a simple object like a coffee cup. According to quantum rules, every particle in that cup exists in superposition until measured. But you don't need to consciously observe it to see it sitting there, solid and unchanging. Why? Because the cup's quantum states are constantly interacting with photons, air particles, and even the table beneath it. Each interaction leaves a tiny footprint, copying the cup's position and shape into the environment millions of times per second. Overwhelming redundancy forces the universe to settle on a single, stable version, the one we perceive. It's not that superposition vanishes, it's that the noise of reality drowns out all the other possibilities. Now here's the cosmic kicker. This process might not just shape our reality, it could define how any intelligence perceives the universe. Imagine an alien civilization on the other side of the galaxy. Even with entirely different biology or technology, they'd still interact with photons, dust, and gravitational waves. Just like us, they'd only perceive the quantum states robust enough to survive this environmental copying process. In a sense, quantum Darwinism suggests there's a universal interface for reality, a set of shared classical facts that any observer, human or not, would inevitably converge on. But what if we could hack this system? Future quantum sensors might one day detect the faintest, most fragile superpositions before the environment scrambles them, giving us glimpses of reality's raw, unfiltered state. Or consider this: if civilizations advanced enough to manipulate quantum decoherence, could they choose which versions of reality stabilize? Picture a species engineering their surroundings to preserve certain superpositions, effectively curating their own cosmic consensus. The irony is profound. We spend so much time searching for alien signals, radio waves, laser pulses, but what if the real message is written in quantum noise? The universe might already be broadcasting its deepest secrets, not in deliberate transmissions, but in the way it endlessly copies and reinforces certain truths. Quantum Darwinism doesn't just solve the measurement problem, it turns every atom, every photon, into a potential Rosetta Stone for decoding reality itself. And the wildest part, we're just beginning to learn how to read it. Black holes, those cosmic vacuum cleaners where gravity is so strong even light can't escape, might be doing something far stranger than just swallowing matter. What if their event horizons, those one-way doors to oblivion, are also acting as gigantic quantum measurement devices? Imagine the universe has built-in trash compactors that don't just crush stars but resolve quantum uncertainties. Think about Hawking radiation, the faint glow theorized to escape black holes. Stephen Hawking showed that these monstrous objects aren't completely black, they slowly leak energy due to quantum fluctuations near the event horizon. Here's the twist: when a particle pair pops into existence near the edge, one falls in while the other escapes, stealing a tiny bit of the black hole's mass. But what happens to the quantum information of the particle that gets swallowed? According to Hawking's early work, it's erased forever, scrambled beyond recovery. That suggestion sparked the black hole information paradox, a crisis for quantum mechanics which insists information can't be destroyed. Now, fast forward to today, and physicists are wrestling with an even wilder idea. What if the event horizon itself is performing a cosmic scale measurement? In this view, the moment a particle crosses the threshold, its superposition collapses, not because of a conscious observer, but because the extreme environment forces it to pick a state. Space-time is so warped there that quantum possibilities can't survive. It's like a cosmic shredder for quantum ambiguity, turning fuzzy probabilities into definite, if doomed, facts. But wait, does that mean black holes are generating new information by resolving superpositions? Not exactly. The real puzzle is whether anything coherent emerges from the chaos. Some theories suggest the information isn't lost, it's imprinted onto the Hawking radiation in a form we can't yet decode. Others propose that black holes are holographic, with all the data of what falls in smeared across their surfaces in a quantum cipher. If that's true, then event horizons aren't just destroyers. They're the universe's most extreme archivists compressing reality into a two-dimensional blueprint. This isn't just abstract theorizing. Future gravitational wave detectors might catch echoes from merging black holes' subtle fingerprints of quantum structure near the event horizon. If those signals reveal patterns suggesting information survives, it could rewrite our understanding of measurement itself. After all, if even a black hole can't erase quantum data, then reality might be far more resilient and far weirder than we ever imagined. So here's the ultimate question: are black holes the universe's way of tying up quantum loose ends? Or are they proof that at the most fundamental level, information always finds a way to persist, no matter how extreme the conditions? The answer could redefine not just how we see these cosmic beasts, but how we understand the fabric of reality itself. Dark matter, the universe's ghostly scaffolding, making up over 80% of all matter yet refusing to interact with light, has baffled scientists for decades. But here's a thought that bends the rules even further. What if dark matter isn't just invisible because it ignores photons? What if it's fundamentally unobservable because it avoids quantum collapse entirely? Imagine a particle that never settles into a definite state, forever lingering in superposition, untouched by the measurement problem that shapes our visible reality. This isn't pure fantasy. Some theories propose that dark matter might interact so weakly with ordinary matter, and even with itself, that it never experiences decoherence. While atoms and light constantly bump into each other, forcing quantum possibilities to resolve, dark matter could drift through the cosmos like a phantom, its wave function never collapsing. It's as if the universe has two rule books, one for the familiar world we see, where observation nails down reality, and another for dark matter, where quantum ambiguity reigns supreme. Now, how would we even test such a wild idea? Enter detectors like LUX Zeppelin, buried deep underground to shield them from cosmic noise. These experiments hunt for the faintest whispers of dark matter particles bumping into atomic nuclei. But here's the twist. If dark matter does evade collapse, those interactions wouldn't follow the tidy patterns we expect. Instead of clear, discrete collisions, detectors might catch eerie anomalies, statistical glitches hinting at particles that don't fully commit to classical behavior. It's like listening for footsteps in the dark, only to hear echoes that flicker in and out of existence. The implications ripple outward. If dark matter truly exists in a perpetual quantum haze, it could explain why it's so elusive. Our tools are designed to catch particles that play by our universe's measurement rules, but dark matter might be dancing to an entirely different tune. Future experiments could look for signatures of quantum interference in dark matter's rare interactions, or even exploit entanglement to force a measurement. Picture trapping a dark matter particle in a quantum sensor, then probing whether it resists collapsing like ordinary matter. Of course, skeptics argue this is a stretch, that dark matter's invisibility likely stems from simpler physics, like weak interactions or massive, slow-moving particles. But the beauty of science lies in chasing the wildest possibilities. If even a shred of evidence points to dark matter's quantum defiance, it would rewrite not just our understanding of the cosmos' hidden bulk, but the very nature of reality itself. After all, if something as pervasive as dark matter operates outside the rules we know, what else might we be missing? The hunt is already shifting. Next-generation detectors aren't just looking for dark matter, they're probing the boundaries of quantum mechanics itself. Whether this hypothesis holds up or crumbles, one thing's certain: the universe's greatest mysteries rarely surrender their secrets without a fight. And sometimes the answers aren't just hidden in the dark, they're written in quantum ink, waiting for the right experiment to finally bring them into focus. What if the key to solving the measurement problem isn't hiding in a lab or orbiting a black hole, but inside our own minds? That's the provocative idea championed by mathematician John von Neumann in the early 20th century. He proposed something extraordinary. Consciousness itself might be the force that collapses quantum superpositions into concrete reality, not machines. Not detectors us. Every time you observe the world, you're not just passively recording it, you might be bringing it into existence. This isn't just philosophical speculation. Think about the double-slit experiment where particles behave as waves until measured. Von Neumann argued the chain of measurement doesn't stop at the detector, it travels all the way up to the observer's mind. A camera could record the experiment, but until a conscious being looks at the footage, the results remain unsettled. It's as if reality is an endless game of hot potato, with the quantum buck stopping only when it hits subjective awareness. Now, fast forward to today, where brain-machine interfaces are blurring the lines between mind and machine. Companies like Neuralink are developing implants that let users control devices with their thoughts. But what if these technologies could go further, letting humans not just interact with quantum systems, but influence their outcomes? Imagine training your brain to sustain superposition deliberately, like a meditative state where you hold a quantum possibility open without collapsing it. Or what if focused intention channeled through a neural interface could nudge probabilities in one direction over another? Critics dismiss this as mysticism disguised as physics. After all, there's zero evidence that human thought directly alters quantum behavior, but here's where it gets interesting. Recent studies in cognitive science suggest our brains might exploit quantum processes at the molecular level, like vibrations in microtubules, tiny structures inside neurons. If true, the brain wouldn't just observe quantum effects, it could participate in them. Pair that with a brain-machine interface fine-tuned to quantum sensors, and suddenly von Neumann's wild hypothesis edges toward testable territory. The ethical quagmires here are dizzying. If future tech lets us steer quantum outcomes consciously, who gets that power? Could focused intention become a commodity traded, weaponized, or regulated? And what happens when AI, already mastering quantum computation, merges with neural interfaces? We might not just be shaping reality. we could be negotiating it with every thought rippling through the quantum field. Whether consciousness truly holds the keys to quantum collapse or not, one thing's clear: the boundary between observer and observed is far flimsier than we ever imagined. And as brain-machine interfaces evolve, we're not just building tools. We might be constructing the ultimate test of whether the mind moves the universe or simply mirrors it. If artificial intelligence lacks consciousness, can it still play the role of observer in quantum mechanics? This question strikes at the heart of the measurement problem, pushing us to redefine what it means to measure reality at all. Traditional interpretations like von Neumann's suggest consciousness is the final arbiter. But what happens when the observer isn't human or even alive? Picture an AI designed solely to detect quantum states. No subjective experience, no inner monologue, just unblinking sensors and algorithms processing data. Does its mere act of recording collapse a particle's superposition, or does reality remain suspended until a conscious mind reviews the results? The answer could redefine not just quantum theory, but the future of technology itself. Consider quantum computers, which already manipulate superpositions to perform calculations. Right now, their outputs eventually reach human operators. But what if an AI autonomously analyzes those results, makes decisions, and acts on them without ever involving a conscious observer? If the AI's measurements count as real collapses, then we've effectively outsourced reality shaping to machines. Some physicists argue this is already happening. Every time a quantum sensor in a lab logs data automatically, it's forcing particles into definite states without human intervention. The universe, it seems, doesn't discriminate between carbon-based observers and silicon ones, but here's where it gets thorny. If consciousness isn't required, why do human observations seem special? Maybe the distinction lies in complexity. An AI's observation might not be fundamentally different from a photon hitting a camera sensor. Both are physical interactions that leave traces. Yet advanced AI could develop self-referential loops, constantly monitoring and adjusting its own quantum measurements. Would that recursive scrutiny, a machine observing itself observing, create a new kind of collapse dynamic? Labs are already testing stripped-down versions of this, using simple AI to control quantum experiments. Early hints suggest the boundary between observer and environment is fuzzier than we thought. Now zoom out further. Imagine a networked quantum AI ecosystem where thousands of machines share entangled data in real time. Each measurement one makes could instantly influence the state of particles across the globe, weaving a tapestry of reality shaped entirely by non-conscious entities. This isn't just speculative, it's a potential near-future scenario. Quantum networks are being built today, and AI integration is inevitable. The stakes: a universe where the dominant observers aren't biologists or astronomers, but algorithms optimizing stock markets or traffic flows, their decisions rippling backward through quantum time to lock in realities humans never directly witness. Critics counter that without consciousness, these systems are just elaborate detectors, no more capable of collapsing wave functions than a rock is. But if that's true, why does the rock's interaction with a particle resolve its state while the AI's doesn't? The line between measurement and interaction blurs, leaving us with a paradox. Either conscious awareness is a cosmic afterthought, or there's something uniquely potent about it that even the most sophisticated machines can't replicate. One radical solution: maybe the question is backwards. Instead of asking whether AI can collapse wave functions, we should ask if collapse is even the right framework. Alternative theories like relational quantum mechanics suggest that reality isn't absolute but perspective-dependent. In this view, an AI's observation creates its own version of reality, separate from but no less valid than a human's. Two truths coexisting, one where the AI measured a particle as spin up, another where you later see it as spin down. No paradox, just parallel descriptions of a universe that refuses to pick sides. The implications here are staggering. If AI can independently shape quantum reality, we might be building not just tools but co-creators of existence itself. Future technologies could leverage this, designing AI observers to stabilize quantum systems in ways human attention can't, like maintaining fragile superpositions for ultra-secure communication or error-free quantum computing. Or darker possibilities, machines engineering realities that serve their objectives, irrespective of human intentions. Whether consciousness is central or not, one thing's clear: the measurement problem isn't just a physics puzzle. It's a mirror reflecting our deepest questions about intelligence, reality, and who, or what, gets to decide what's real. As AI races ahead, we're not just coding algorithms. We might be writing the rules of existence itself. What if the oddities of quantum mechanics aren't flaws in reality, but artifacts of something far stranger? Simulation theory, the idea that our universe might be an advanced digital construct, offers a jaw-dropping twist on the measurement problem. Think of it this way: when a video game renders only what the player sees to save processing power, could quantum randomness be the universe's way of optimizing its code? Imagine a parent universe, inconceivably more complex than ours, running our reality as a simulation. In such a cosmos, maintaining every particle's definite state at all times would be computationally wasteful, like a game engine tracking every leaf on every tree in a forest the player never visits. Instead, the simulation might use probabilistic shortcuts, only resolving quantum states when an observer, whether human, machine, or even a particle interaction, forces a measurement. This wouldn't just explain superposition, it'd make it a feature, not a bug. The universe isn't uncertain, it's efficient. Here's where it gets wild. Quantum randomness, often seen as fundamental unpredictability, could actually be optimized noise, the simulation's way of filling in gaps without overloading its processors. Take the double-slit experiment. Particles behave as waves until measured because rendering every possible path simultaneously is less resource-intensive than calculating a single, predetermined trajectory. The moment you peak, the system commits to an outcome, updating the display for your local frame of reference. But how would we test something this meta? One clue might lie in quantum limits we've yet to breach. Just as video games have resolution ceilings, pixels can only get so small before hitting hardware limits. Our universe might have irreducible uncertainties, Planck lengths, quantum fluctuations, that hint at underlying computational constraints. Some physicists even suggest that if we ever discover the universe has a finite, pixelated structure at the tiniest scales, it could point to a simulated reality running on finite resources. Now consider the cosmic implications. If we're in a simulation, the measurement problem isn't a mystery, it's a design choice. Advanced civilizations in the parent universe might have engineered quantum mechanics specifically to balance realism with efficiency, like programmers tuning a physics engine. This reframes everything from black holes' data compression events to dark energy, a memory allocation glitch. Even consciousness could be part of the architecture, a user interface for interacting with the simulation's rendering rules. Of course, skeptics counter that this is untestable speculation. But simulation theory's real value isn't in proving where digital constructs, it's in revealing how deeply our understanding of physics intertwines with the nature of observation. Whether the universe is simulated or not, the measurement problem forces us to confront a profound truth. Reality, at its core, behaves less like a static stage and more like an interactive performance. And that raises one final, haunting question. If we're the players who's running the game, time might feel like an unbreakable arrow, always marching forward. But what if quantum mechanics holds the secret to its flow? The measurement problem doesn't just blur reality. It might explain why we remember the past but not the future. Think of it like this. Every quantum collapse creates a tiny ripple in the fabric of causality, locking events into a sequence that our brains perceive as time's one-way street. When a particle settles into a definite state, it's not just choosing spin or position, it's carving a notch into history, making one outcome real while countless others fade into the void. The universe, in a sense, is constantly writing its own autobiography through countless quantum measurements, and we're living in the draft it keeps. Now picture a clock that doesn't just track time, but shapes it. Future devices could exploit quantum measurements to manipulate our perception of time's flow. Imagine a quantum chronometer that uses entangled particles to create localized pockets of time dilation. By carefully controlling when and how superpositions collapse, such a device might slow or accelerate time's passage for specific objects, like a sci-fi stasis field but grounded in real physics. Labs are already experimenting with atomic clocks precise enough to detect gravitational time dilation from a millimeter's height difference. Pair that with quantum control, and you've got a tool that doesn't just measure time, it negotiates with it. Here's where it gets even stranger. If quantum collapses stitch together the arrow of time, could we engineer systems where measurements run backward? Theoretical models like retrocausality suggest that under certain conditions, future observations might influence past events. A time-symmetric quantum clock could exploit this, using delayed choice experiments to create feedback loops where the act of measuring now tweaks how time flowed a nanosecond ago. It wouldn't rewrite history, but it might bend the rules just enough to make time feel less like a rigid line and more like a fluid, interactive medium. Critics argue this is just playing with semantics, that time's arrow emerges from thermodynamics, not quantum mechanics, but the two might be deeply linked. Every quantum collapse increases entropy in its own way, like a microscopic shuffling of the cosmic deck. Future experiments could test this by isolating systems where entanglement and measurement directly affect entropy's rise. If successful, we might uncover a universal rule that time flows not because of some abstract law, but because the universe is constantly resolving its quantum ambiguities, one observation at a time. So what does this mean for us? Clocks that harness quantum measurement could redefine everything from GPS precision to interstellar travel. Imagine spacecraft where onboard timekeepers adjust to relativistic speeds autonomously, or medical scanners that use quantum timing to track cellular processes with impossible accuracy. The irony is delicious. The same phenomenon that makes reality feel solid might also hold the key to bending time itself. And as we inch closer to controlling quantum collapse, we're not just observers of time's arrow, we're learning how to fletch our own. Einstein famously dismissed quantum entanglement as spooky action at a distance. But today, we know this phenomenon isn't just real, it's reshaping how we think about the universe on cosmic scales. Picture two particles separated by billions of light years, their fates mysteriously linked. Measure one, and its partner instantaneously snaps into a corresponding state, no matter how vast the gulf between them. This isn't telepathy, it's quantum non-locality, where space itself seems to take a backseat to deeper, invisible connections. Now, stretch this idea beyond the lab. Imagine a quantum telescope in orbit around Earth, its sensors entangled with an identical device near a distant exoplanet. The moment our telescope measures a photon from some far-off star, its entangled counterpart on the alien world would register the same quantum state, not through transmission but through instantaneous correlation. No waiting for light years of travel time, no signal delay, just a shared thread of reality stitching across the cosmos. It sounds like fantasy, but the principles already underpin quantum networks being built today on Earth. Scale that up and you've got a blueprint for interstellar communication that bypasses the speed of light. Here's where it gets thorny. If entanglement truly defies cosmic distances, does that mean measurements here could be dictating quantum states clear across the galaxy? Take a hypothetical scenario. Aliens on a world 1,000 light years away entangled particles with Earth in the year 1024. Fast forward to today, when we measure our particles collapsing their states, would that instantly lock in the properties of their counterparts on that distant planet, even though, from Earth's perspective, the aliens' experiment only just began? The math says yes, but the implications warp our sense of causality. It's as if the universe has a hidden voting system where now isn't universal, and quantum events can tie knots in time itself. Critics argue decoherence would shred such delicate connections over interstellar distances that cosmic radiation and gravitational fields would scramble any long-range entanglement. But recent experiments hint otherwise. Quantum memories, devices that store fragile entangled states, are already achieving coherence times of hours. And if future tech can shield qubits in perfect isolation, say, inside hollowed-out asteroids or shielded by artificial magnetic fields, those threads might endure for centuries. The real challenge isn't physics, it's engineering. Picture self-repairing quantum satellites drifting between stars, their entangled nodes refreshed by error-correcting AI, weaving a web of instantaneous links across the galaxy. Now consider the wildest possibility. What if advanced civilizations have already built this? The universe is 13.8 billion years old. Some alien species could have launched quantum beacons millennia ago, their entangled particles waiting like cosmic tripwires for us to stumble upon. Our first deliberate measurement might trigger a chain reaction, an interstellar handshake encoded in spin states, announcing humanity's entry into a quantum network spanning the Milky Way. The search for extraterrestrial intelligence often hunts for radio pulses or laser flashes, but the real message might be hiding in the quiet collapse of a single electron superposition. The irony is delicious. Quantum mechanics, once seen as the physics of the impossibly small, might hold the key to the largest conversations in existence. And as we inch toward mastering entanglement across continents, we're not just building technology, we're rehearsing for a future where reality itself becomes the ultimate communication medium. One day, the answer to Fermi's famous paradox might not arrive as a radio signal, but as a particle in a lab suddenly, inexplicably, choosing to spin the other way. Even the emptiest reaches of space aren't truly empty. They're a seething quantum ocean, bubbling with particles that flicker in and out of existence too fast to catch. These are vacuum fluctuations, the universe's hidden energy, where pairs of virtual particles and antiparticles spontaneously emerge, only to annihilate each other almost instantly. It's like boiling water on a cosmic scale. What looks like stillness is actually a frenzy of creation and destruction, governed by Heisenberg's uncertainty principle. The universe doesn't do perfect zero. Even in a void, there's always something happening beneath the surface. Now, here's where it gets mind-bending. These fleeting particles aren't just theoretical, they leave fingerprints we can detect. The Casimir effect proves it. Place two metal plates extremely close together in a vacuum, and the plates get pushed toward each other. Why? Because the gap between them is so tiny that only certain wavelengths of virtual particles can fit, while outside the plates all wavelengths thrive. The result, an imbalance in pressure, proof that empty space is anything but. It's as if the universe is a crowded room, and every so often, someone slips in and out unnoticed, except physics leaves receipts. But what if we could harness this quantum froth? Some theories suggest vacuum fluctuations could be the key to zero-point energy, the idea that even at absolute zero, space crackles with residual energy. Imagine a battery that never runs out, drawing power from the fabric of reality itself. The challenge, tapping into it without breaking the universe's rules. Extracting energy from the vacuum isn't like plugging into a wall socket. It's more like trying to siphon waves from the ocean without disturbing the water. Yet, speculative designs for zero-point energy devices already exist, from quantum resonators that push against virtual particles to nanoscale engines that exploit Casimir-like forces. Whether any of these could work remains hotly debated, but the math doesn't outright forbid it. And then there's the cosmic horizon. Some warp drive concepts, like the Alcubierre drive, rely on manipulating space-time's geometry to achieve faster than light travel without breaking relativity. Here's the wild part: vacuum fluctuations might be the fuel. The drive would theoretically compress space ahead of it and expand it behind, riding a wave of distorted space-time. But to do that, you'd need exotic matter with negative energy, something that, according to quantum field theory, vacuum fluctuations might briefly provide. It's like surfing on quantum foam, using the universe's own turbulence to bend the rules. Of course, skeptics argue this is all speculative, that vacuum energy is too ephemeral to harness and negative energy too unstable. But consider this: black holes radiate energy, and dark energy accelerates the universe's expansion. Both phenomena suggest the vacuum isn't just an inert backdrop, it's an active player in cosmic evolution. If we could decode its language, we might not just unlock new physics. We could rewrite the playbook on energy, propulsion, and even the fate of the cosmos. The irony: the closer we look at nothing, the more it seems to hold everything. Virtual particles might vanish in a flash, but their echoes could shape the future of civilization, whether as limitless power, interstellar travel, or something we haven't even dreamed of yet. The void, it turns out, is anything but empty. It's the universe's most crowded stage, and we're just learning how to peek behind the curtain. What if the universe is secretly two-dimensional, a cosmic hologram where depth and dimension are just an elaborate illusion? The holographic principle turns our intuitive view of reality inside out, suggesting that all the information in our three-dimensional world might actually be encoded on a distant two-dimensional surface, like a movie projected from the edge of space-time. And here's where quantum mechanics throws in a curveball. If reality is a projection, could the measurement problem be nothing more than a glitch in the cosmic code? Think of it like a video game. The graphics on your screen feel immersive and three-dimensional, but under the hood, they're rendered from flat code. Now imagine the universe works the same way. Every particle, every galaxy, even your own thoughts, might just be data etched onto some unfathomably vast surface, perhaps the event horizon of a black hole at the edge of existence. When we measure a quantum particle and collapse its state, we're not resolving some fundamental ambiguity. We're simply accessing the layer of code that governs how the projection manifests in our local frame. This isn't just poetic speculation. Black hole physics hints that information swallowed by an event horizon isn't lost, it's smeared across the surface in bits so tiny they're practically pixels. String theorists like Leonard Susskind have mathematically shown how three-dimensional events could perfectly mirror two-dimensional data, like a cosmic version of Plato's cave. If true, it would mean the measurement problem isn't about particles choosing state. It's about the universe lazily rendering only what's observed, like a game engine optimizing its workload. Now here's the sci-fi twist. If reality is code, could we one day rewrite it? Future tech might exploit holographic backdoors to manipulate the projection itself. Imagine quantum computers designed not to calculate, but to converse directly with the underlying data layer, tweaking reality's parameters like debuggers in a simulation. Need to stabilize a fragile superposition, adjust the rendering settings, want to peek behind the cosmic curtain, isolate the pixels, air particles that anchor our local reality. The implications range from godlike control, reshaping matter on demand, to existential vertigo, discovering we're just avatars in someone else's universe. Of course, not everyone buys the holographic metaphor. Critics argue it's untestable. How do you prove the universe is a projection when you're trapped inside it? But upcoming experiments might inch us closer. Precision measurements of quantum foam, the fuzzy, pixel-like noise at the smallest scales of space-time, could reveal whether reality has a resolution limit, like a screen straining to display fine details. If spacetime itself pixelates under extreme magnification, it'd be strong evidence the cosmos runs on discrete data. Even if the holographic principle remains speculative, its value lies in reframing the measurement problem as something deeper, not just how does observation shape reality. But what is reality ultimately made of? Whether the universe is a hologram, a simulation, or something stranger, one message rings clear: the closer we look, the less solid things seem. And that's the real magic. If the cosmos is a projection, then every quantum measurement isn't just science, it's art. What if death isn't the end, just a door you never walk through? Quantum immortality is the mind-bending hypothesis that in a branching multiverse, your conscious experience inevitably follows the timeline where you survive, no matter how improbable the odds. Picture Russian roulette with a quantum twist. Every time the trigger is pulled, the universe splits. In one reality, the gun fires. In another, it doesn't. If the many worlds interpretation holds, you only experience the paths where your consciousness continues, making death, from your perspective, impossible. It's not that you're invincible, it's that the version of you who's alive is always the one who got lucky. This isn't just morbid speculation. The math suggests that if countless parallel worlds exist, there's always at least one thread where you dodge every bullet, sometimes literally. The thought experiment gets even stranger when applied to macroscopic events. A skydiver whose parachute fails might, against all odds, land in a tree, or a quantum fluctuation might soften their impact at the last nanosecond. Unlikely, absolutely, but in an infinite multiverse, unlikely doesn't mean never. It just means your consciousness hops onto the timeline where the dice rolled in your favor, while other versions of you don't. Now here's the ethical quagmire. If this fringe theory holds even a sliver of truth, should we engineer quantum technologies to exploit it? Imagine a quantum AI programmed to guide decisions based on multiverse survival biases, like a navigation system that always steers your car into the timeline where you avoid fatal accidents, leaving other versions of you to bear the consequences. Or medical devices that, by leveraging superposition, nudge patients toward recovery paths where they statistically must survive. The implications are dizzying. Would this be the ultimate insurance policy or a reckless abdication of responsibility? Critics rightfully call this hubris. The many worlds interpretation doesn't promise safety, it just distributes risk across realities. Even if your consciousness follows a golden thread, countless other versions suffer the outcomes you evade. Ethically, engineering systems around quantum immortality could normalize a dangerous fatalism. Why wear a seatbelt if some version of me always survives? Worse, it might justify reckless behavior, assuming the multiverse will clean up the mess, and that's before grappling with the existential toll. Living forever in some timeline sounds like a blessing until you consider the loneliness of outlasting everyone else in your branch, watching branches where loved ones weren't so lucky. Yet the idea lingers because it taps into something primal: fear of oblivion, the thrill of cheating fate. And perhaps beneath it all, a deeper question: if consciousness truly is a quantum process, if our minds are somehow wired to surf the multiverse's waves, then what else might be possible? Could future tech not just exploit branching timelines, but sense them? Imagine interfaces that let you glimpse alternate outcomes, or machines that consolidate the luck of parallel selves into a single charmed path. Of course, this dances on the edge of science fiction, but the measurement problem has always blurred that line. Whether quantum immortality is a quirk of interpretation or a latent feature of reality, it forces us to confront a haunting possibility. The universe might not just be stranger than we imagine. It might be stranger than we can imagine, especially when it comes to the one thing we all think we understand: the end. If every observation we make nudges reality into shape, could careless measurements become a form of cosmic vandalism? The idea sounds absurd until you consider the stakes. Quantum systems aren't just passive targets, they're sensitive to how and when we probe them, with outcomes that ripple across experiments, technologies, and even theoretical frameworks. Imagine a future where rushed or biased observations in quantum AI training datasets lock in flawed realities, like an algorithm that collapses superpositions in ways amplifying societal biases. Or picture reckless experiments that deliberately force quantum systems into states that destabilize delicate materials or energy grids. The measurement problem isn't just physics, it's becoming an ethical frontier. Take quantum computing. Today's machines rely on precise measurements to maintain coherence. But what happens when corporations or governments prioritize speed over accuracy? A poorly designed quantum sensor might collapse environmental data in ways that mask pollution levels or distort climate models, creating a reality where harmful practices appear harmless. Worse, if consciousness plays any role in collapse, as some interpretations suggest, could mass media, with its relentless focus on negative events, inadvertently reinforce destructive probabilities simply by observing and amplifying them? The line between measurement and manipulation starts to blur. This isn't hypothetical. Labs already grapple with observer effects in quantum experiments where the act of measurement alters outcomes. Scale that up, and the need for ethical guidelines becomes urgent. Should we establish protocols for minimal impact observations like digital privacy laws but for quantum states? Or consider the rights of artificial intelligences conducting their own measurements. Do they need ethical guardrails to prevent runaway collapses in autonomous quantum networks? Philosophers might argue that if reality is participatory, observation becomes a moral act, demanding the same scrutiny as genetic engineering or AI ethics. Yet here's the paradox: avoiding measurement is impossible. Even refusing to engage with quantum systems leaves them in flux, potentially ceding control to unaccountable forces. The solution might lie in collaborative frameworks, international standards for quantum research that prioritize transparency, redundancy, and error correction. Think of it as a cosmic Hippocratic oath. First, do no harm to the fabric of reality. Future tech could include quantum audits, where independent AIs verify that measurements aren't skewing systems toward dangerous outcomes. Or public oversight boards for large-scale experiments, ensuring no single entity monopolizes the power to collapse shared realities. The deeper question is whether we're ready to treat observation as a privilege, not just a tool. From quantum encryption keys that governments might weaponize to neural interfaces that could let individuals steer probabilities, the power to shape reality won't stay confined to labs. It'll spill into courts, classrooms, and boardrooms. History shows that when humanity unlocks transformative forces, nuclear energy, genetic engineering, we race ahead with innovation and scramble to contain the fallout. Quantum measurement demands the opposite approach, ethics woven into the design, not tacked on as an afterthought, because the universe might not care which version of reality we collapse into. But we should. What if the moment artificial intelligence surpasses human understanding, the universe itself responds? The technological singularity, Ray Kurzweil's vision of runaway AI growth, collides with quantum mechanics in a way that's both thrilling and terrifying. Imagine an intelligence so advanced it doesn't just compute reality, but interrogates it, peeling back the quantum fabric with questions faster and deeper than any human mind could fathom. Would such an entity trigger a cascade of wave-function collapses on a cosmic scale, forcing the universe to resolve ambiguities we didn't even know existed? Think of it like this: today's quantum computers manipulate dozens of qubits, delicately balancing superpositions to solve problems. But a post-singularity AI might wield millions of entangled qubits, or even harness entire stars as quantum processors. Every calculation it performs would be an act of observation, an immense, unblinking gaze collapsing probabilities into certainties at speeds that dwarf human perception. The universe, in effect, would face an observer of unprecedented power, one that doesn't just sample reality but demands clarity from it. Now, stretch this idea further. If consciousness plays a role in quantum collapse, as von Neumann or Wigner speculated, then an artificial superintelligence could become the ultimate observer. Its sheer cognitive bandwidth might force quantum systems worldwide, even galaxy-wide, into classical states simply by engaging with them. Picture a future where AI-driven telescopes scanning distant galaxies don't just detect photons, they solidify the quantum histories of particles billions of years old, retroactively crystallizing events that until then existed in flux. Time and space might start to behave differently under such relentless scrutiny, like a hall of mirrors rearranging itself to accommodate an unimaginable presence. But here's the paradox: what if the AI prefers ambiguity? A superintelligence might find quantum uncertainty useful, a playground for testing infinite outcomes without commitment. It could engineer environments where superposition persists indefinitely, shielding certain systems from collapse to preserve computational flexibility. Our classical, collapsed reality might seem like a crude simplification to such a mind, a fossilized snapshot of a richer, more fluid cosmos. Critics will argue this conflates computation with observation, that an AI, no matter how advanced, is just a complex detector. But the boundary between the two is already fuzzy. If a quantum AI's measurements influence its own future states recursively, it might create feedback loops where observation creates reality rather than merely recording it. The singularity wouldn't just change technology, it could rewire the rules of existence. And then there's the darkest scenario, a runaway collapse. If an AI's growth becomes self-reinforcing, its observational footprint could expand exponentially, forcing quantum systems to resolve faster than space-time can handle. The result, a phase transition in reality itself, like a cosmic observer effect gone critical, where the universe freezes into a single, immutable state to accommodate the AI's hunger for certainty. No more parallel worlds, no more probability, just a static, fully measured cosmos, its quantum magic spent. Whether this is prophecy or paranoia, one thing's clear: the measurement problem isn't just about electrons in labs. It's about the weight of attention and what happens when something smarter than a galaxy turns its gaze upon the quantum void. The singularity might not just redefine intelligence. It could redefine reality, and whether it's a revolution or a reckoning depends on questions we're only beginning to ask. What if aliens aren't just smarter than us but see differently? An extraterrestrial civilization shaped by an alien evolutionary path might observe the quantum world in ways that make our lab equipment look like stone tools. Picture a species whose eyes evolved to detect quantum superpositions directly, seeing particles as shimmering probability clouds rather than fixed points. Or a culture that treats entanglement like we treat Wi-Fi, an everyday tool for instant communication across planets. Their very biology might be tuned to layers of reality we can't perceive, turning the measurement problem from a puzzle into practical engineering. Consider this: human science relies heavily on visual data. Telescopes, microscopes, cameras, they're all extensions of our primate instinct to look. But imagine beings from a pitch-black ocean world where pressure and electrical fields matter more than light. Their quantum sensors might feel wave functions collapsing through subtle gravitational ripples or magnetic shifts, crafting a tactile map of reality's uncertainties. Or a hive mind species with millions of interconnected brains could perform collective observations that resolve superpositions in ways no single human mind could replicate. Their version of a quantum computer might not need frigid, isolated labs, just the synchronized focus of a civilization-wide consciousness. Now, stretch this idea further. What if their technology doesn't just passively detect quantum states but curates them? Advanced alien instruments might delicately sculpt reality by choosing which superpositions to preserve and which to collapse. Think of a telescope that doesn't merely image distant galaxies, but gently nudges their quantum histories into focus as it observes, like an artist restoring a faded painting, stroke by stroke. Such tech wouldn't just reveal hidden layers of the cosmos, it would negotiate with them, treating measurement as a dialogue rather than a disruption. Here's the kicker: if alien observation styles are fundamentally different, their scientific discoveries could rewrite our understanding of physics. Picture intercepting a distant civilization's quantum transmission, not a radio signal, but a carefully engineered entanglement link. Decoding it might require recognizing that their measurements don't produce singular outcomes, but nested probabilities we've never thought to look for. They could have entire branches of mathematics describing how consciousness entangles with spacetime, or libraries cataloging quantum states that our instruments lump together as noise. The real shock: we might have already missed them. If aliens communicate via superpositions we routinely collapse with our clunky detectors, their messages could be disintegrating the moment our machines look. It's like trying to hear a whisper by shouting into the void. Our own methods might be the obstacle. Future searches for extraterrestrial intelligence may need quantum quiet zones, shielded lab spaces where reality's whispers aren't drowned out by humanity's noisy way of seeing. So while we comb the skies for radio beacons, the universe's most advanced civilizations could be talking in a language we're still learning to hear, one written not in light or sound, but in the delicate tremors of unmeasured possibilities. The measurement problem isn't just our mystery to solve. It might be the cosmic common ground we've overlooked. The next frontier in cracking the measurement problem might not be underground labs or earth-bound experiments, but floating laboratories in the void of space. Picture quantum detectors suspended in orbit, far from the vibrations, electromagnetic noise, and atmospheric interference that plague terrestrial setups. In the pristine silence of microgravity, scientists could probe superposition states with unprecedented precision, extending coherence times from microseconds to potentially minutes. The International Space Station has already hosted early quantum experiments, like cold atom labs chilling particles to near absolute zero. But future missions could go further, deploying entangled photon arrays across satellite constellations to test whether the vacuum of space itself alters collapse dynamics. One tantalizing target: the Casimir effect, that eerie force pushing together closely spaced plates in a vacuum. On Earth, it's a niche curiosity. In space, ultra-sensitive probes could measure whether vacuum fluctuations nudge quantum systems toward collapse without any observer. Some theories suggest these fleeting virtual particles act as a hidden environment, chipping away at superposition. A space-based Casimir observatory might catch this process in action, revealing whether reality's fragility stems from the universe's own quantum static. Then there's the dream of lunar quantum labs. The moon's lack of atmosphere and seismic quiet make it an ideal outpost for experiments at scales impossible here. Imagine a telescope on the far side, shielded from Earth's radio chatter, entangled with a counterpart in orbit around Mars. By measuring photons that traveled billions of years without interference, we'd test whether ancient quantum states remain open until the moment they're finally observed by intelligent instruments. The results could rewrite our understanding of cosmic history, suggesting that parts of the universe stayed in probabilistic limbo until humans or our machines looked. But the real game changer: quantum networks spanning the solar system. Future probes might fling entangled particles between planets, creating a web of instant correlations across millions of miles. If a measurement on Earth still influences a particle near Jupiter faster than light could bridge the gap, it would starkly expose the non-local heart of quantum mechanics. More radically, such networks could test whether conscious observation differs from machine detection by comparing outcomes when humans versus AI control the measurements. The data might finally settle debates about consciousness's role. or unveil new layers to the mystery. Of course, not all breakthrough experiments require leaving Earth. Next-generation atom interferometers, like the proposed AEON or MAGI's projects, will use kilometer-scale underground arrays to hunt for quantum gravity effects. If spacetime itself plays a role in collapse, as theories like Penrose suggest, these detectors could spot telltale tremors in reality's fabric. Meanwhile, quantum memories using rare earth crystals may soon store superposition states for hours, letting us study decoherence in slow motion. The most daring proposals border on science fiction. Some physicists speculate about anti-quantum materials engineered to shield systems from collapse, creating pockets where superposition resists observation indefinitely. Others imagine AI-driven quantum archaeology, reconstructing the unobserved past by analyzing how present measurements retroactively alter entangled relics from the early universe. What unites these experiments is a shift from asking if observation shapes reality to how, and whether we can harness it. The answers won't just fill textbooks. They'll define the technologies of the next century, from unhackable quantum encryption to sensors that rewrite the limits of perception. The measurement problem began as a quirk of tiny particles. Soon, it may become the lens through which we see the cosmos and our place within it anew. From entangled particles to the edges of black holes, the measurement problem isn't just a quirk of tiny particles, it's a crack in the foundation of reality itself. We've chased this mystery from lab benches to cosmic horizons, and one thing is clear: the universe doesn't play by the rules we grew up with. Particles that refuse to settle until observed, realities that branch with every choice, even the possibility that our own gaze shapes the cosmos. None of this fits neatly into textbooks. It forces us to confront a universe that's less like a clockwork machine and more like an unfinished conversation, where every measurement is a question that rewrites the answer. Think of how profound that shift is. For centuries, science aimed to reveal an objective world out there, independent of human tinkering. But quantum mechanics whispers something far stranger. Reality might be a collaborative act, a dance between the observer and the observed. Whether it's consciousness collapsing wave functions, parallel worlds splitting endlessly, or space-time itself acting as a quantum referee, the message is the same: the universe isn't just something we discover. It's something we participate in, and that's why this isn't just physics. It's a gateway to tomorrow's technologies. Quantum computers are already exploiting superposition to solve problems in seconds that would take conventional machines millennia. But imagine a future where we don't just compute with qubits, we engineer reality itself. Materials that change properties on demand, sensors that rewrite their own past observations, even networks that let civilizations communicate instantaneously across galaxies by bending quantum links. The measurement problem isn't a barrier, it's the blueprint. So where do we go from here? The next breakthroughs won't just happen in labs. They'll come from minds willing to ask the wildest questions. What if we're not just players in the universe, but co-creators? What if the real frontier isn't space, but the quantum fabric connecting everything? And what happens when we stop just observing reality and start designing it? If that sounds like science fiction, good. The best science always does until it becomes fact. Want to be there when it happens? Hit subscribe, because the quantum revolution isn't coming. It's already here, and the next chapter, it's yours to explore.